For more than a century, chemists believed that neutral nitrogen molecules beyond N2 could never exist. Too unstable, too reactive, gone in an instant. But in 2025, a team of researchers did what many thought was impossible. They isolated a new allotrope of nitrogen, hexanitrogen N6, a molecule with enough stored energy to rival the most powerful explosives known, yet stable enough to observe, measure, and even hold in a thin film. A discovery that rewrites the chemistry of the element that makes up 78% of our air. Nitrogen, despite filling the atmosphere, is surprisingly boring. As N2, two nitrogen atoms triple bonded, it's famously inert. It doesn't burn, doesn't react, and doesn't pollute. This is why nitrogen-based fuels are considered a dream for clean energy. They store enormous chemical energy but release only harmless N2 when they decompose. But there was a catch. Scientists could imagine bigger nitrogen molecules, N4, N6, even N12. But they could never make them. Neutral allotropes simply fell apart before anyone could see them. Only fleeting radicals like N3 had ever been identified, and only in the gas phase. Hexanitrogen, N6, was a theoretical curiosity, computed thousands of times but believed too unstable to ever hold still, until now. In their landmark 2025 study, Weiyu Qian, Artur Mardukov, and Peter Schreiner reported something extraordinary: the creation and characterization of neutral molecular N6 at room temperature. Their approach didn't rely on extreme pressures or exotic equipment. Instead, a gas phase reaction produced a species that had never been isolated before. The secret wasn't in forcing N6 to exist, but in catching it quickly enough to study it. The products were trapped inside solid argon at 10 Kelvin, just a few degrees above absolute zero. Here, the elusive molecule finally stood still long enough for science to see its fingerprints, and what they observed was unmistakable. Infrared spectroscopy revealed 4 vibrational bands unlike anything attributed to known nitrogen species. Ultraviolet visible spectroscopy confirmed electronic transitions predicted only for N6. Isotope labeling, replacing specific nitrogen atoms with heavier isotopes, produced the exact spectral shifts theory demanded. Theory and experiment aligned perfectly. For the first time, the chemical world had direct spectroscopic evidence of a neutral N6 molecule. Even more surprising, the researchers were able to prepare a thin film of pure N6 at 77 K, the temperature of liquid nitrogen. This suggested that N6 isn't as fragile as once thought. It has a real, though limited, lifetime. According to high-level quantum chemical calculations, N6 adopts a C2H symmetric structure, a chain of 6 nitrogen atoms with alternating double and single bond character. Its weakest points, the N2, N3, and N4, N5 bonds, form the molecule's Achilles heel. Yet the overall structure requires a substantial barrier to fall apart into the stable N2 molecules we breathe. That barrier is high enough to give N6 a measurable lifetime. At room temperature, milliseconds. At liquid nitrogen temperature, more than a century. This is a metastable molecule, one that shouldn't last long, but lasts long enough. The decomposition of hexanitrogen into 3 molecules of N2 is immensely exothermic, releasing over 185 kilocalories per mole. Weight for weight, this is 2.2 times the energy of TNT and nearly twice that of high-performance explosives like RDX and HMX. It is, by calculation, one of the highest energy materials ever synthesized, a clean energy candidate that releases only nitrogen gas. The discovery of N6 is more than a chemical curiosity. It challenges the long-held belief that neutral polynitrogens beyond N2 are too unstable for direct observation. It opens the door to new energy storage concepts based on materials that are powerful yet environmentally benign. And it provides the first experimental bridge between theoretical nitrogen chemistry and reality. A molecule predicted for decades, now finally seen. From the air we breathe to the molecular architectures we imagine, nitrogen has always seemed familiar, even simple. But hexanitrogen proves that the element still holds secrets. Somewhere between theory and experiment, impossibility and discovery, lies a new landscape of chemistry, and N6 is only the beginning.